Hey ChemStars, it's Miss McCauley here bringing you your Chapter 21 video notes on nuclear chemistry. We're going to start out at Chapter 21, Section 2.1, radioactive decay. Here's the I can statement for this section. I can recognize the four types of radioactive decay: alpha, beta, gamma, and positron. So in this section, the key vocab to focus on is alpha, beta, gamma, positron, and those are all types of radiation. We're going to start with a little bit about the history. I'm not going to go too much into the history in these video notes, but there's going to be more info posted on Google Classroom. So if you go to Google Classroom, has more info. Your teacher will post some other historic videos and things there. So let's start off first with Roentgen. He discovered X-rays in 1895. Our next scientist was Becquerel, and he discovered radioactivity in 1896, but didn't know it yet, wasn't quite sure what he was seeing. The most important scientists we have would be Marie and Pierre Curie. They discovered what caused Becquerel's discovery and later discovered radium and polonium. And we'll definitely go into that more later in class. And then a review from last chapter, Ernest Rutherford. He's the one that used alpha particles to discover the nucleus in his famous gold foil experiment. He discovered different types of rays in 1899. So a lot of these discoveries were happening at the end of the 1800s. Okay, so let's go on to what is radioactivity actually. It's a process by which an unstable nucleus emits one or more particles or energy in electromagnetic radiation. So let's go through and break that down a little bit. So key words here are unstable nucleus. If you look back at your PhET lab from chapter 3, where you built your own atoms, you had to do some things to make the nucleus unstable. You either had too many protons or too many neutrons, and that forces it to undergo nuclear decay. It emits one or more particles. Those particles could be alpha, beta, neutrons, or positron particles. And or it can also emit electromagnetic radiation. We're going to focus on gamma radiation in our nuclear unit. Okay, let's scroll down a little bit here. So then let's look at some other things here with the nuclear radiation. So nuclear radiation, that is the charged particles and or the energy. So those unstable nuclei can give off both or one or the other when they are unstable. As it decays, that radiation leaves the nucleus as the particles or as the energy. So particles or energy. Here's an important thing I want you to highlight. Radioactive decay is spontaneous and does not require any input of energy. So you can't control it, you can't predict it, it is spontaneous. Another key vocab word is radioisotope. It's the nuclei of unstable isotopes. So let's break down that new vocab word. Radio and the radioisotope, that implies that it's radioactive, and we saw that the radioactive part means that it's unstable. So radio means it is radioactive, unstable. The second part there, we have isotope. An isotope is an atom with a specific mass. So we're looking at the radioactive nuclei of these unstable atoms. Okay, let's see here, our next section. Differences between chemical reactions and nuclear reactions. So almost all year in chemistry, except for this chapter, we will exclusively deal with chemical reactions. And these are all about losing, gaining, or sharing the valence electrons. This is an important vocab word from 9th grade physical science, or maybe 8th grade science. Those valence electrons, those are the outermost electrons in an atom. So just the ones on the very outside. These can be affected, so they are affected by changes in temperature, pressure, or catalysts, and they can give off or they can absorb energy. Either thing is possible. So that's what most of our year will be focused on. However, in this chapter, we are focusing on those nuclear reactions from the radioisotopes. In nuclear reactions, atoms gain stability by undergoing changes in the nucleus. So we're going to the very heart of the atom. Either the protons, neutrons, or both will change in that radioisotope. They are not affected by temperature, pressure, or catalysts. Like we said, it is spontaneous and does not require any inputs. It always gives off tremendous amounts of energy, like we saw in the fallout video. So remember the fallout video we watched, where we saw the nuclear bomb tests. Okay, flip the page, please. Okay, let's look at some types of those radioactive particles that are going to be given off. So the first one we're going to look at is an alpha particle. An alpha particle is like a helium nucleus. If you look at your periodic table, you'll see that helium's atomic mass is 4, atomic number is 2. So a helium atom would have 2 protons, 2 neutrons, and if it's neutral, it would then, of course, have 2 electrons. But we're saying it's just like the nucleus. So there are no electrons in the alpha particle. So if we look at that charge, there's 2 positives and 2 neutrals. That means that helium is going to have that positive charge of +2. So the mass number for an alpha particle is 4, made up of the 2 protons and the 2 neutrons. The atomic number is 2. There's 2 protons. There are 2 neutrons, and the charge is a +2. The other way you can draw it, you can always write the alpha particle like this, or you can show it as a symbol here, alpha. And then you also would include the mass is 4 and the charge is a +2. Right here is an example I want you to take a look at. So if we have uranium-238, it's very unstable. The ratio of protons and neutrons is not good enough for it. So to get more stable, it kicks out an alpha particle, and what's left over has a different atomic number and becomes thorium-234. Here's something I want to call your attention to. Remember, like I taught you in conservation of mass, treat the arrow like an equal sign. Let's look at the mass on both sides of the equal sign. The uranium has a mass of 238. It becomes thorium-234 and helium with a mass of 4, which also is 238. So did I conserve mass? Yes. The second thing to call your attention to is that we also will be conserving the atomic number or the charge. So uranium on the left has a charge of 92. There's 92 protons. And look at the right. Thorium has 90 protons, and the alpha particle has 2 protons. That's also 92. So in these nuclear reactions, make a note here, nuclear reactions conserve mass and charge. That's something new we haven't seen before. We're conserving charge. The symbol that might not have printed on your notes here, that is 4,2 alpha. That's a congruent, that's a similar way. You can either write it like this, or you can write it with that helium symbol. Okay, let's move on to the beta particles now. Those are pretty much just the same thing as an electron. So if we take a look at these beta particles are pretty much just fast-moving electrons. As you recall from chapter 3, electrons have no mass, or their mass is so small it's almost 0. We're going to skip atomic number. I'm going to come back to that. How many neutrons do electrons have? None. They're electrons. What is the charge of an electron? -1. So this is what's going to bring us to the atomic number. Electrons and protons have opposite charges. So before, when we had like 2 protons, it was a 2 atomic number. Now when there's 1 electron, we're going to say technically that's a -1 charge. The symbol that we'll use here is this is the symbol for the positron. So what do you think the symbol for the electron would be? We're going to use this beta symbol. It's the Greek letter. Mass is 0, charge is -1. So that is your beta particle. The opposite of a beta particle, it's like an opposite electron. So we call it a positron. If you can guess from that name, it's the same thing as an electron, but it has a positive charge. So here's an example of beta decay. If you have radioactive carbon-14, it's unstable, and it spits out a beta particle, which you can see right here. It's an electron, and it leaves over a mass of 14, a charge of 7, and it becomes nitrogen. So like I taught you a little bit earlier, nuclear reactions conserve mass and charge. Let's see if that's true for our other example. So treat the arrow like an equal sign. On the left, the mass is 14. On the right, we have a mass of 14 and a mass of 0. So we started with 14 mass units and we ended with 14 mass units. Let's look at the charge then. On the left, we have a charge of 6. On the right, we have a charge of 7 and -1. 7 and -1, that's 6. So in this example, we conserve charge as well. And if you look here, the symbol that might not have printed, it's the beta symbol. So just make a note. A beta forms as a result of breaking apart a neutron in an atom. So how do we get this beta particle? One of the neutrons in this carbon nucleus underwent this reaction where the mass of one became split. So we have one mass over here, we have 0 and 1, we've got one mass on this side. There was no net charge, but you know that neutrons are actually made up of smaller particles called quarks. Something happened there in the nucleus, and we got a proton and an electron. If you have a -1 and a +1, that's really a 0 charge. So that checks out with our conservation of mass and our conservation of charge. Let's take a look at what happens when radioactive nuclei emit neutrons. That can also be a way to get more stable. So in that case, it just throws out a neutron. Neutrons are neutral. That means there is no charge. So the mass of one neutron is 1. The atomic number, there isn't one. There is no charge. There are no protons because it's a neutron. There's one neutron and the charge is 0. So let's go to the next page and look at when radioactive nuclei give off energy. So a lot of times the atom will be giving off energy as well. The type we're going to focus on is called gamma radiation. The symbol for gamma is this Greek letter. It looks kind of like an upside down cursive L. It is not matter. It is pure energy. So it is a pure photon of energy in the electromagnetic spectrum. We haven't covered this yet, but in chapter 4, we're going to look at all the different types of electromagnetic radiation. Visible light is just a small portion we can see. So we'll cover this in chapter 4. You've probably heard of infrared or microwaves or radio waves. Those have lower energy. Higher energy things include UV light, which is what sunburns you, X-rays, like you get at the doctor's office, and then gamma radiation is very, very, very energetic, and it's what can damage your DNA and cause some radiation sickness. So that gamma particle, it's not a particle, it's pure energy, but we kind of represent it with that same particle notation we saw on the previous page. So the mass number, 0, there is no mass. The atomic number, 0, there's no charge. Number of neutrons, 0, charge, 0. It is pure energy. Okay, we got another I CAN statement to get through on this video. So I CAN recognize the 4 types of radioactive decay: alpha, beta, gamma, and positron. So I'm hoping that after watching these videos, you could give a brief description of each type. And there's a second thing we're going to look at. It's what you need to do to block each type of radiation. So let's look at this diagram. So if we have a source, a radioactive source material right here, insulated by lead, and it's shooting out alpha, beta, and gamma particles, if you put a strip of paper in between you and that source, only the beta and gamma will get through. That means that paper effectively can block alpha particles. So your skin actually can block alpha particles, and that's why in the Fallout video they were brushing off the soldiers with a broom. Let's say you're behind a wooden door. If you look at what gets through the wooden door, only gamma particles get through. We're going to say maybe it's about a 1-inch thick wooden door. So that can block the beta or the positron particles. And then let's see, lead or concrete. Is that enough to block all the gamma? Not quite. Some still gets through. So this will block some gamma, and we'll go over in class how much you actually need to protect you from all types of radiation. So let's rank those from least to greatest penetrating power. So your skin will block alpha particles. If you get to the inside of a building, you'll be safe from beta, but to effectively block gamma, you need to have some real insulation between you and the radioactive source. Okay, so last thing I'm going to do in this video is we are going to summarize what we learned so far. I've got about a minute left, so we're going to try and get through these real quick. So the alpha particle, the symbol we use is alpha 4-2. It is made up of 2 protons and 2 neutrons. The charge is a +2. The mass is 4 because there's 2 things there. A common source of that, you don't have to memorize these things, but a common source of that is polonium-210. And another common source is uranium-238. Penetrating power is low. A piece of paper will block it. So to shield yourself, all you need is paper, or your skin will actually shield you from that. Next one I want to look at is beta radiation. We got the beta particles, and we also have the positrons. So it's either an electron or it's a positron. So I'm just going to kind of